Paul is the variety and breadth of the research that he became involved with as a student here. So he actually got involved in several observational projects, collaborating with people like Lisa Cooley and Sarah Ellison and Dave Patton, and finished a number of papers on the work that he did with them that's not even part of his thesis. But of course, this required him to make great sacrifices, taking many lengthy trips to places like Hawaii and Australia in order to collaborate with people like Lisa and her collaborators. And somehow, on top of that, he actually managed to find some time to do some theoretical work too, which is the subject of what he'll talk about today. And this work, I think, is really elegant. It talks about new models for understanding galaxy formation and evolution that are based on state-of-the-art computer simulations that I think provide a step beyond what's been done in this field up to now. And so, based on the success that he has had and the breadth of his work, it's not surprising that he did very well on the job market this year. And in fact, he got several offers from top places around the country, and in the end couldn't actually decide where he wanted to go. And so what he did was to actually accept 2 independent offers that run at the same time, one from MIT and one from Caltech. And I'm not sure what his main motivation for this was, if he wanted to collaborate with Mark Vogelsberger at MIT and Phil Hopkins at Caltech, or if he wanted to be able to escape to LA during the winters in Boston and escape to Boston during the summers in LA, or if he was really angling to try and collect 2 salaries simultaneously. So I hope he worked out the details of that with the people that are actually hiring him. So without further ado, I'll let Paul talk to you now about what he's done in his thesis. And like I said, I think it's a very impressive piece of work.
Thank you, Lars. Yeah, thank you very much for that very kind introduction. And thank you all for being here. This is actually quite a turnout for this sort of talk. So it's a pleasure to have so many people in the room to be able to talk about the work we've done over the recent years on my PhD dissertation. So most of the stuff I'm going to talk about is work modeling the properties of galaxies within cosmological simulations. And our principal goal, what we're shooting for here, is to try to make increasingly realistic galaxy populations that form directly in cosmological simulations so that we can assemble a more coherent theory of galaxy evolution. And all this work has been advised by Lars Hörnquist. But before talking about the actual science for today, I wanted to take a minute to actually send out some acknowledgements. So first and foremost, I want to thank my family, Mom and Dad. Yeah, I'm very grateful that you guys are here. Mom, save those tears. We might need them later, depending on how things go. I appreciate you guys. So I'm very grateful for you guys supporting me throughout. So I tried to find a way to actually express the way these guys have actually supported me over the past 27 years. And I was looking really for something concrete to show to you guys. And I found this picture of me at space camp. So this was me in 4th grade going to space camp. But this is just really an example of how my parents have supported me over the past 27 years. I'm very grateful. Lars, yeah, thanks a lot for the support you provided. So the time I've spent here in graduate school has been really wonderful. And in particular, I've seen myself grow as a researcher, and that's owing to your guidance and support. So I'm very grateful for that. Mark and TJ Cox. Mark and TJ served as the role of, one could say, principal contacts for a lot of the science projects that I worked on. These were the guys that I went to when I wanted to figure out how to develop some new analysis pipeline or how to actually set up something on a new computer that I hadn't dealt with before. These guys gave very practical information to help me get going on a lot of the projects. So I'm very grateful to your help. The postdocs. So there's been a number of postdocs who have passed through Lars's group in the ITC over the past several years. And all of them, at one time or another, have opened their door to provide either scientific guidance or professional guidance for me. And so I'm very, very grateful to all their support. In particular, we got Dusan Karas, Deborah Shiatchki, and Patrick Janssen, who have since moved on from the ITC. Then we got Shai Ganel, Annalisa Filipich, Laura Salas, and Thomas Greif, who are still here as members of the ITC and working with Lars's group. To my TAC committee, several members are here today. Dan Eisenstein, Ido Berger, and Ramesh Narayan. Thanks for providing support throughout and providing professional guidance to help shape the content of this thesis and ensure that I was, in fact, marketable when it came time to apply for jobs. To my senior collaborators, so as Lars mentioned, there's been a number of observational folks that I've worked with, Lisa Cooley, Dave Patton, and Sarah Ellison, who have given real direction to some of the projects that I've worked on. So we have these powerful galaxy formation models the question arises, how do we want to apply them? How do we want to extract the most information? And these guys constantly had ideas about how we could do that. Also, Volker Springel, who's been a great mentor and scientist to have involved with this research. He's provided not only hands-on assistance in terms of running some of these simulations, but also provided great ideas about how to approach some of the science that we've been doing. I've got a list of professional mentors, Arjun Day, who's here joining us today, as well as Chung-Pei Ma and Rob Simcoe. These guys have all taken time out of their schedule to talk to me largely about professional development, and I've been really appreciative about that. With each of them, I've been able to talk about not only science that's ongoing, but how I can develop myself as a researcher in the field. To the department administrators, got Nina, Peg, and Rob listed here. Thanks a lot for all your support. I mean, these guys have been key. They've ensured that I've been a registered student for the past 6 years. They've ensured that I actually get paychecks when the time comes. Really, the amount of work they do to help make sure that my graduate student tenure has been successful is large, and they've done it the whole time with a smile on their face. So I'm very grateful for all of the help you guys have provided. To the non-astronomer crowd, there's several folks who actually are here today, either took days off from work or traveled from New York or other places. Thanks a lot for the support you guys provided throughout. So graduate school is a tumultuous time. You actually end up going through some highs and lows, and throughout that whole time, I've had a lot of fun hanging out with you guys, trips to New York or when you guys finally moved back to Boston. So thanks a lot. And to the astronomers, there's definitely a lot of acknowledgements required there. The CFA has a very special graduate student community. And there's two groups I wanted to particularly highlight. The first group is my class cohort, so the folks that I actually entered in with. I think we were fairly lucky, actually. We ended up having a group of people, not that were any better than others, but which got along really well. The transition to grad school with you guys by my side was a lot of fun. I really enjoyed that. And the other cohort I wanted to recognize is the graduate students who have passed through Lars's group, who I've recently been told are sometimes called conquistadors. Don't know if you know that. So this has been a hugely supportive group of researchers. We're very involved with what everyone else is doing. We're constantly updated on who's struggling with what parts of the code and who's actually working on what projects. And it's a lot of fun working in that dynamic environment. So I'm very grateful to all members of that group and the rest of the graduate student community as well. This is a very special place to go through graduate school. So I had to put up a couple of pictures from just a sampling of the sort of things that I've gone through in graduate school and some of the fun memories. We've got trips to Heidelberg from this recent trip in September with Shai and Mark and Lars when we were going out to work out some of the details of one of our most recent cosmological simulations. We've got times had at local bars. I think this was after someone's thesis defense. Chris showing off the bill money as if he's now suddenly rich. ITC cups, playing soccer with the folks here. That's been a lot of fun. Nights out with friends in New York. And nights out with friends around Boston. So with that, I'll start pushing into the more scientific content of this talk. And I want to start by actually getting rid of one of your ideas, which is that I do anything related to the actual real universe. In fact, the majority of work that I'll talk about is theoretical in nature. So what we're doing here is trying to assemble a theory of how to interpret what people see in the night sky. The majority of what I'll talk about is actually work done within simulations. And so, okay, as this cartoon kind of depicts, what we're not actually doing is looking at the night sky, but trying to build a framework which helps us get more information out of the observations that do exist. So to put this into a picture, this is showing in a single slide. Let me see if I can bring the lights down here as well. Is that too dark? Okay. So this is showing in a single slide the motivation for this talk. This is showing the Hubble Ultra Deep Fields. And when you look at an image like this, you're actually seeing not just the abundance and variety of galaxies as they exist in our universe, but actually the entire evolutionary picture of what's going on within galaxy formation and evolution. So to explain this to the non-astronomers in the room, you can look at this picture in a different way. You can kind of tilt it on its side. And what you're seeing here is a timeline going from the Big Bang to the present day. At early times, you had a nearly homogeneous distribution of gas, a nearly smooth distribution of gas and dark matter in the universe. And over time, you find that structure forms through gravitational collapse, which builds up the complex distribution of galaxies that we see in the local universe. There's this novel aspect of our universe that light travels at a finite speed. And so as you look at patches of galaxies that are nearby, you find the time it takes a photon to travel to our telescope is relatively small. That means that we can see these galaxies as they exist more or less today. If we push that slice further out, the time it takes a photon to travel to our telescope is a bit longer. And so we're actually looking at these galaxies as they existed a while ago. And as you push back further and further, you begin to see galaxies as they existed sooner and sooner after the Big Bang. So when you actually look at this image, you're not just seeing galaxies in the nearby universe like this guy here and this guy here. You're actually seeing all these dots, all these small things being galaxies throughout cosmic history. So our goal is to try to take an image like this and assemble a theory which tells us how we're actually populating the abundance and variety of galaxies as a function of time. Now, the actual approach that we take towards doing this is to run cosmological simulations. To do that, we start from initial conditions in the early universe, where we have information about the initial density fluctuations in the matter field. We can then build a simulation which includes the relevant physics. And I'm going to come back to what exactly relevant physics means in a couple of slides. But in particular, what I mean by that is gravity, hydrodynamics, and then higher order effects, things like star formation, feedback from supermassive black holes, etc. Then what we do is we allow the galaxies to self-consistently evolve within the simulation and compare it back against what's actually seen in the real universe. By comparing our simulated galaxies to what's actually observed, we can then basically redefine what we think relevant physics is. We can see areas where our simulation is doing well and areas where it has failed, and try to augment the physics in our simulations to improve the models that we're building. By doing this in a repetitive process, you end up basically improving or building ever more realistic models of what the galaxy distribution looks like in the real universe, but within our simulation. And the reason why that's powerful is that we can then fast forward, we can rewind, we can actually see how galaxies are assembling their properties. So to show animation of what this actually looks like, this is showing a fly-through of one of our cosmological simulations. And what you're actually seeing here is the gas distribution within this volume. This is a galaxy here. You've got galaxies dotting the background along these filaments, which are known as the intergalactic medium or the cosmic web. This galaxy is growing in time. It's accreting gas from its hot halo, or the reservoir of gas that surrounds it. It's also having accretion events like that there, where you actually have satellite galaxies being accreted onto this central galaxy, delivering gas. And this is all starting from initial conditions that were nearly homogeneous. This structure has been developing self-consistently in time, basically under the influence of just gravity and hydrodynamics. And so we can learn a lot about the role that, for example, galaxy mergers or interactions play, how galaxies are building up in different environments, just by using these sorts of simulations as probes of the relevant physics for galaxy formation. Now, in terms of what the relevant physics is here, and this will actually somewhat trace the logic of this talk, I think it's important to understand that there's a logical flow to what's important for building up galaxies. This is not a path forward, but rather a pyramid. Okay? So at the base of this pyramid, what we have is gravity. Gravity is the single most important factor in determining structure formation in the universe. The structure formation proceeds by assembling dark matter halos under gravitational collapse. After you have an accurate gravity solver in your simulation, you can then move on to including hydrodynamics. Hydrodynamics are the next most important factor in determining how gas, or baryons, get into our galaxies, assemble gas disks, form stars, and so forth. And then as you move beyond that, I have the nebulous other physics. This is where all the messy stuff goes from astrophysics. This is where star formation, feedback from black holes, radiative cooling of gas, etc. go. And there's a logical flow here. You really can only move on to dealing with these more complicated processes after you have a solid base for your simulation code. And part of what I'll talk about during this presentation is how we've done some work on stabilizing the hydrodynamic portion of this pyramid and how we can then build on top of that to form very realistic galaxy populations. So to give you guys a preview about where this talk is going, this is showing now the real Hubble Ultra Deep Field, which I showed you on the motivation slide, compared against a mock Hubble Ultra Deep Field. They're going side by side, so you can basically compare the number density of galaxies, the colors of galaxies, and the sizes of galaxies. And what you can generally gather from this is that overall, when you compare the properties of these two images, we've now obtained a fairly good match between the distribution of galaxies in our mock Hubble Ultra Deep Field, which is taken from one of our cosmological simulations, compared against the real Hubble Ultra Deep Field. So the basic outline for this talk is to tell you the story of how we've gotten there. That's going to come in three parts. The first is a discussion of the role that hydrosolvers play in building up gas disks within galaxies. The second point is a discussion of the role that feedback plays in regulating the growth of galaxies after gas has gotten into the central part of these halos. And then the third part is going to be a discussion of how we can maximize the comparisons that we can do with observations by bridging the gap between simulations and observations, by building up mock image catalogs. So because this is a largely theoretical or numerical talk, I wanted to start by saying a couple of words about our methods. And as Lars mentioned, we've been using a principally new method to the field of galaxy formation. That's a simulation code known as Arepo, which applies a fundamentally new hydrosolver to this field. To understand why it's new, we can talk first about the traditional methods that people have applied. One method is known as a Lagrangian-based method. This has been realized in codes that use smooth particle hydrodynamics. One in particular is the code Gadget. This is very, very widely used. In fact, papers show up on arXiv at least weekly using this simulation code. And the key step that's taken here is that you discretize your fluid into a series of mass resolution elements. You discretize it into a series of simulation particles, if you will, and you allow those simulation particles to move throughout the simulation domain. You can think of this as discretizing a river into a bunch of macroscopic fluid elements and watching them flow together. All right? These types of codes have a couple of advantages which are particularly important for galaxy formation. First of all, they're geometrically flexible. So as you have gas flowing into a galaxy, it might first pancake or turn into a filament, fill out a sphere, turn into a disk. It can handle all these geometries very easily along the way. This type of code is naturally adaptive in terms of its resolution. So as particles move into a halo, you find that as the gas density increases in the central parts of these galaxies, that your number of resolution elements also increases. So you have adaptive resolution. And they have this unique property that they're Galilean invariant. What that means is that if you have a galaxy which is being attracted towards, say, some group or cluster of galaxies, it might have some large bulk velocity. And this will be handled naturally in these Lagrangian methods because the hydrodynamic equations of motion will not feel that large bulk scale velocity. The other type of methods that have been applied are these Eulerian methods. And these have been implemented into codes through a method known as AMR, or adaptive mesh refinement, for example, ENSO. The fundamentally different approach here is that rather than discretizing my fluid, I now discretize my volume. And I now watch the fluid flow across some grid. So I basically lay down a fixed grid and I watch the river flow across it. In practice, what we do here is that we take a grid like this and we solve the Riemann problem at all of the cell interfaces. We find out how much mass, momentum, or energy is flowing across all of these cell boundaries. Now, because of the nature of the Riemann problems that are applied in these types of simulations, you find that they're pretty good at handling instabilities. They're good at capturing shocks in a natural fashion, and they're very good at capturing sharp phase boundaries between, say, a hot and cold phase that are next to one another. Now, Arepo falls somewhere in between these two types of methods. We call it a quasi-Lagrangian finite volume method. And what it attempts to do is take the principal advantages of Lagrangian methods and the principal advantages of Eulerian methods and combine them into a single hydrosolver. So what's done here is that you have a series of mesh resolution points, or mesh generating points, that are shown as these teal dots. And you allow these mesh generating points to move throughout your simulation according to, for example, the fluid flow. But when it comes time to actually solve the hydrodynamic equations of motion, you discretize the volume using a Voronoi tessellation based off of the distribution of those mesh generating points. You then take all of these cell interfaces and solve the Riemann problem across those cell interfaces. So you have a Lagrangian method by allowing the mesh to move with the fluid flow that then applies a Eulerian type Riemann solver to actually solve the hydrodynamic equations of motion. If you look at this in practice, this is a two-dimensional Kelvin-Helmholtz instability. At relatively low resolution, far away from the billows that are developing, you see that these cells are basically just advecting with the fluid flow. They're actually not changing their shape all that much. However, if I now look close to where the billows are developing, I find that these cells can be changing their shape continuously to account for the movement of mesh generating points around them. They're also changing their color. In this simulation, color is showing density, so these are actually advecting mass across their cell boundaries. Now, in test problems, we can show very easily that Arepo has a lot of demonstrated advantages in terms of how it's able to handle a lot of hydrodynamic phenomena. But the real question we have for today, and where I've contributed some work, is to look at how Arepo performs on galaxy formation problems. So this has been work that's been done with a lot of folks who are here at the CFA, some who have moved on since, within the context of the Gadget Arepo comparison project. So the specific task that we set out for here was to compare the performance of two simulation codes that are nearly identical in all of their characteristics except for the hydrosolver that they apply. So Gadget and Arepo are both written by Volker Springel. They have nearly identical backends. So they use the same gravity solver, they start from the same initial conditions, and they include the same physics, things like radiative cooling of gas, star formation prescriptions, etc. The only real difference between these two codes is the hydrosolver they apply, and it's a radically different hydrosolver. So we can basically run two side-by-side simulations and see how the hydrosolver is impacting the resulting galaxy populations that form. Now, if we do that, this is the result. This is a plot taken from a paper by Mark Vogelsberger. On large scales, this is showing the gas distribution in Arepo on the left and in Gadget on the right. And these two plots look nearly identical. The reason for that is that on large scales, the gas distribution is very similar between these two codes because it's driven by the gravitational collapse of structure. Hydrodynamic phenomena are subdominant on these large scales. As you push down towards the halo scale, what you find is that, again, you're looking at Gadget on the left. We've got a temperature plot and a density plot of the gas. We find that the halo gas around galaxies in Gadget is hotter and is more abundant than the halo gas around the same galaxies in Arepo. And if we push down to even smaller scales, we look around the galaxies themselves, what we find is that the spatial distribution of gas within Arepo tends to be smoother and more spatially extended than the counterparts in Gadget. And this is the scale where I focused my attention. So if you look at a number of galaxies, that was for one specific example, you find this is a ubiquitous result. That galaxies, the gas disks in galaxies can be substantially larger in Arepo compared to their matched companion in Gadget. So you have all this gas in the halo in Gadget, which is basically here just showing up in a gas disk. This is showing for 5 examples, but in fact you can generalize this and show that in this simulation volume this is true for hundreds, if not thousands, of galaxies. So what's actually driving these differences? Well, at the time when we first were doing this comparison project, it was somewhat unclear what the major differences between these two codes were. However, in hindsight, there's a lot of very obvious tests you can do which show that you shouldn't expect at all to get the same answer between these two codes. One example is looking at a Kelvin-Helmholtz instability. So this is showing a Kelvin-Helmholtz instability. I'm going to have dense fluid moving to the right here and diffuse fluid moving to the left here. These 3 panels just show Kelvin-Helmholtz instabilities with different thicknesses for the inner band. That's the only difference. On the top, I've got Arepo, and on the bottom, I have Gadget. So one might imagine this could represent cold gas coming in from the intergalactic medium flowing into the CGM hot halo. Well, what happens in these two simulations? In Arepo, we find that we have billows developing, which quickly shred the cold material and efficiently mix the two phases. In Gadget, we find that an artificial surface tension term tends to stop mixing between these two phases, and we end up getting to building up these blob-like structures, which don't mix almost at all with the diffuse hot gas. So what's the result in cosmological simulations? Well, this now shows a cutout from one of the systems within the comparison project. We're showing large-scale gas distributions here on the left. We have nested views going down to small-scale gas distributions on the right. From the first snapshot, you can see we have relatively large gas disks in Arepo, but what I want you to focus on is all the blobs that exist down here. These blobs, you can watch their subsequent evolution, where they're actually going within this simulation. In fact, these blobs are very efficiently migrating to the bottom of this potential well. What's happening is that these start as mild overdensities in the IGM that fall into the circumgalactic medium, or the hot halo, and are pressure confined. That causes them to radiate away their energy. And while they should be disrupted due to Kelvin-Helmholtz and Rayleigh-Taylor instabilities, those instabilities are suppressed in Gadget. As a result, they lose their orbital energy and angular momentum to hydrodynamic drag, and they end up providing a source of cold, low angular momentum fuel to these central galaxies. So whereas my primary mode of accretion over here is cooling from the hot halo, here I have an additional channel of accretion, which is from these cold blobs as they migrate to the center of this potential well. And that can be quite profound in terms of the ending properties of these galaxies. Now, to make the comparison a bit more statistical, we actually fit exponential profiles to the gas disks in these two simulations. So this is showing the central surface density versus the disk scale length from these simulations. The gas disk best fit parameters for Arepo are shown in red, and the best fit parameters for Gadget are shown in blue. You can see a histogram up here which shows the projected distribution of those disk scale lengths. There's a clear offset. where the disk scale lengths for the Arepo galaxies are substantially larger than those that you find in Gadget. And so that's a reflection of the images that I've shown you previously. So we can really break this down at the end of the day and ask what drives these differences. Well, I talked, for one, about fluid instabilities. That plays a really central role. The inability of Gadget to disrupt the cold gas as it comes into these hot halos is fairly disruptive to the gas disks that form. And if you want to have more spatially extended gas disks form in Gadget, you have to improve the way that fluid instabilities are handled there. There's a second effect, which I didn't yet talk about, but I'll mention here. It's the viscous heating of halo gas. So what happens here is that turbulent power is injected around the virial shock. When you inject that energy, it should cascade down to smaller scales. But rather than it cascading down in Gadget, what you actually find is there's a truncation of the turbulent power cascade, where you actually end up depositing or thermalizing a lot of that turbulent energy close to the virial shock. That's one of the reasons why you have more gas and hotter gas in the Gadget galaxies compared to the Arepo ones. And then there's the issue with fluid phase boundaries. This one's also fairly severe. What happens is that as you have cold gas disks rotating within hot halos, there's a viscous interaction between those cold gas disks where you basically transport some of your angular momentum to the hot halo. And that torques down the cold gas disk at the expense of the hot halo. So we can ask the question, are all Gadget SPH results wrong? Giving this talk at other universities is actually somewhat fun because now's the time when I get to look out into the audience and see people kind of shift in their chairs nervously, not sure what I'm going to say next. I think we can say no, or not necessarily at least. And there's two specific reasons why. All right, the first is that these results are dependent on the actual formulation of SPH that you use. There's recent work which has really made a concerted effort to try to remove some of these strongest deficiencies in the Gadget hydrosolver. And it's also application dependent. There are certain applications where one can find that the hydrodynamic phenomena that are not handled well in Gadget are simply not present. To provide a concrete example of that, this is work that I did with Chris Hayward looking at mergers between Gadget and Arepo. So here the setup is a lot simpler. It's fundamentally different. We took two isolated galaxies and we set them on merging trajectories. They're going to come together, go by first pericenter passage, form tidal features, and eventually come together for final coalescence. Now we can look at, for example, the star formation rates during this merger sequence. And this is what we find. This is showing the star formation rate as a function of time. And there's actually two lines shown here. There's a Gadget line shown in solid, and there's an Arepo line shown as a dashed line. They're nearly on top of one another. So in this situation, we get a nearly identical result. The evolution of this system is almost completely indifferent to which hydrosolver you're actually using. So what actually gives here? After I just talked about how deficient the Gadget hydrosolver can be in these cosmological simulations, why can we get such great agreement here? The answer is that those hydrodynamic phenomena that we expect to be hurting the Gadget results in a cosmological context are simply not present here. Because we've used isolated galaxies that don't have any diffuse gas around them, there's basically no phase boundaries. We don't have fluid instabilities. There's little or no turbulence in these systems. There's no weak shocks, and strong shocks are handled relatively well by Gadget. And there's no need for mixing. So you end up with an evolution that is indifferent to the differences in the hydrosolver. And so in some cases, you can actually get agreement between these two codes still. But that's a bit of a diversion there. What we actually care about is how Arepo compares to observations. So I've now tried to convincingly argue that, in fact, the results obtained from Gadget simulations are not a good reflection of what should be happening in reality. The question we now have is, do our new simulations agree better with things like the Hubble Ultra Deep Field? Unfortunately, the answer to that is no. So this is showing now the Hubble Ultra Deep Field here that I showed at the beginning in the motivation slide, and I compared against a mock Hubble Ultra Deep Field using these comparison project simulations. The result is that actually the number density of galaxies over here is far higher than the number density of galaxies over here. And the reason for that is that we haven't applied strong feedback yet. In these simulations, we kept them very simple, and without strong feedback, stars form efficiently in almost all halos. So the number density of galaxies over here is far too high than what we expect observationally. Another way to express this problem is by looking at the cosmic star formation rate density. So this is showing the star formation rate as a function of cosmic history. The blue line shows the result from our no feedback simulation, and the black dots show observational constraints. What you see is that we're actually almost an order of magnitude off at redshift 0, and we overshoot at all redshifts fairly substantially. So you can easily conclude from this that star formation is far too efficient. So okay, that's not that big of a problem. We already knew that when we ran these comparison project simulations that the feedback we were using was too weak. So that means that if you look at the stellar mass function or the Tully-Fisher relation or the star formation rate density, you do find that our simulations are not providing good matches to reality. However, up until this point, we have been focusing on a numerical comparison. If we want to push towards producing more realistic galaxy populations, we need to include feedback. And we've specifically done that by including galactic winds and AGN feedback, feedback from supermassive black holes. So the second topic I wanted to cover today is a testing of the feedback physics that we've now included into the Arepo simulation. Now that we have validated, at least in our own minds, the hydro solver that's used in Arepo, we now want to know what happens if we include a complete feedback module. How does that help us form realistic galaxy populations? And again, this is work that's been done with very strong contributions from a number of people here at the CFA. So we've now included a relatively complete physics or feedback module into Arepo. And there's 4 principal contributions to this. The first is a stellar evolution contribution. What now happens is that when stars form in our simulations, we allow aging stellar populations to return both mass and metals to the ISM. On top of that, we have metal line cooling added in, so those metals actually have a dynamical impact on the system, allowing gas to cool more efficiently, especially at 10 to the 5 or 10 to the 5.5 Kelvin. We've got galactic winds included using a kinetic scheme. So as you have ongoing star formation within your galaxy, we kick particles out in order to help regulate the growth of stars within these galaxies. And we've included an AGN feedback scheme. That takes on 3 components. We've got a quasar mode component, where we inject energy thermally when we have high Eddington accretion rates. We've got a radio mode component, where we inject mechanical energy when we have the black holes accreting at relatively low accretion rates. And an electromagnetic component. That's where we change the cooling rates of gas around galaxies under the assumption that they see not only the ionizing UV background, but also the radiation from a nearby quasar. This full physics module has now been run in several simulations. We ran these in 25 megaparsec cubed volumes at 3 different resolution levels. And what I'd really just point out here is that at this highest resolution level, the baryon mass resolution is just over 10 to the 6 solar masses. That means is that we still have large particles relative to, for example, star cluster scales or GMC scales. But we're now down to a mass resolution that's able to resolve fairly well a wide variety of structure within the galaxy stellar mass function in these boxes. So coming back to this Hubble Ultra Deep Field comparison, to get a visual idea about how this actually matters, this is again showing the no feedback case versus the real Hubble Ultra Deep Field. If we include metal line cooling and stellar mass loss, we actually make the problem worse. So this allows us to have gas cool more efficiently, and it increases the supply of gas that's actually available for star formation within the galaxies themselves. If we now turn on galactic winds, that's the most efficient mechanism that we have for regulating the growth of the low-mass galaxies. And that's because we're injecting energy which can more easily help gas escape from low-mass galaxies. The mass loading factor for winds is higher in those low-mass systems. The problem here, though, is that if you now look in the real Hubble Ultra Deep Field, you see that we lack these sort of red guys, the quenched galaxies. When we turn on AGN feedback, that's when we're then able to actually quench some of these systems and form a galaxy population which also has the right colors, especially at the massive end. To make this a bit more quantitative, we can look at the cosmic star formation rate density. This is showing, again, the star formation rate as a function of redshift. This is the plot I showed you before with the no feedback case. If we turn on winds only, what we find is that at early times, we're able to suppress star formation to a level that's fairly consistent with observations. And that's, again, impacting these low-mass systems. These different colored lines show contributions from different mass spins of galaxies. So at early times, we're able to suppress star formation in those relatively low-mass systems as they develop. At late times, we still have a rampant overproduction of stars, with the most massive systems actually contributing to that very substantially. So we, again, need to do something for the star formation for the most massive systems. If we turn on AGN feedback, well, that has almost no effect at early times. However, it allows us to get a late time slope, which is fairly consistent with the observations. So at early times, the black holes have not built up substantial mass, so they can't actually have a significant impact on their host galaxies. But at late times, we basically quench almost all star formation in the most massive systems. So when we include both, that's when we end up with this evolution that passes through the data points at most redshifts. And this is the fiducial model that we use for the rest of these multi-epoch model validation comparisons. Another way to look at this is through the galaxy stellar mass function. So this is looking at the stellar mass function at 4 different redshifts. We've got redshift 3, 2, 1, and 0. The 3 different lines here show our simulations at 3 different resolutions. So the red line is the highest resolution, which you can focus on. At redshifts 3 and 2, we get very good agreement, actually, between the galaxy stellar mass function and the underlying observational data points. At redshift 1, there's actually a bit of a normalization offset between our simulations and the observations. And that's an indication that something happens after redshift 2 by redshift 1 where these systems are actually building up mass a little bit too efficiently. One can imagine trying to fix this by perhaps increasing the strength of feedback, but most likely that would actually then mess up the agreement we had at earlier times. Moreover, if we look at the redshift 0 galaxy stellar mass function, there we find that the overall normalization and the exponential cutoff actually looks fairly consistent with observations. So simply increasing the feedback to correct the behavior at redshift 1 wouldn't necessarily help at these other redshifts. That's a fairly interesting tension. But overall, we get a normalization evolution and exponential cutoff that agrees fairly well with the observations. Another test we can put our models through is looking at the star formation main sequence. So this is looking at the 2D distribution of the star formation rates as a function of mass. The 2D histogram shows where our galaxies actually fall in this space. And the black line shows a best fit. These blue data points show the data that we're actually comparing to, the observational data that we're comparing to. So this is looking at redshift 2, at redshift 1, and at redshift 0. The overall evolution in the star formation main sequence from high redshift to low redshift is dominated by a normalization shift. And that's captured fairly equally well in the simulations compared to what's seen observationally. There's a bit of a normalization offset, which is somewhat interesting, because our galaxies are forming stars a bit too inefficiently compared to their observed counterparts. So that might tend to indicate that we need to do something to perhaps weaken our feedback to boost their star formation rates. Right? This goes in the opposite direction of what we saw in the previous plot. Then you have something like this. This is the mass metallicity relation. This is showing the gas phase metallicity within the star-forming gas as a function of mass. There's 2 sets of data points shown here. And the reason for that is there's uncertainty in the nebular emission line diagnostics that are used to calibrate these metallicity measurements in real galaxies. So these 2 points basically bracket what we think is a reasonable guess for the actual metallicity of star-forming gas in galaxies. What we're trying to do is match the shape that's seen here and get somewhere between those 2 sets of points. So at redshift 2, we do a fairly good job in terms of coming in with the correct shape and normalization for the mass metallicity relation. But as we push down to redshift 0, what you find is that the slope here is actually far too steep. And this is actually a direct reflection of our feedback model, a really interesting tension, actually. What's happening here is that for low-mass galaxies, we know that we require strong feedback to regulate the growth of these systems. That same strong feedback tends to eject not just all the mass from these systems, but all the metals as well. And so you end up depleting the metal content of these low-mass galaxies, and that inhibits the buildup of metal content here, which is actually seen observationally in terms of the evolution of the mass metallicity relation. So there's a somewhat subtle tension there where, while we require strong feedback to actually regulate the stellar mass growth of these galaxies, that can have implications in the metallicity content, which is not necessarily favorable. So a summary of the findings from this particular section is that with this feedback model, we actually have a fairly successful model. It's able to regulate the evolution of the cosmic star formation rate density. We now have a galaxy stellar mass function that agrees fairly well with observations across several redshifts. And we have a Tully-Fisher relation, though I didn't show it, that has normalization and slope that is fairly agreeable with observations as well. I think there are some really interesting tensions that remain. One is with this overproduction of galaxies around redshift 1, right? This might indicate that we actually need to include slightly stronger feedback in order to help suppress the formation of those galaxies. We've got the normalization of the star formation main sequence, which might tell us that we need maybe a bit weaker feedback. These two obviously going in opposite directions. And then we've got the shape and normalization of the mass metallicity relation, which may tell us that we need to think carefully about whether our kinetic winds are fully capturing the feedback mechanisms that regulate real galaxy growth. But overall, it shouldn't be ignored that this actually is one of the most successful hydro simulations at reproducing such a wide range of galaxy relations across so many different redshifts. In fact, if you look in the literature, most simulations that are published have a hard time capturing even the most simple of these relations, like the galaxy stellar mass function. So this is really quite a step forward in terms of our ability to produce realistic galaxies within cosmological simulations. So with that full feedback model in place, our next goal was to try to extract as much information as possible, to try to bridge the gap between our simulations and observations. And the way we want to do that is to convert our simulations into mock data products. We want to basically use the same tools that observers would try to derive physical properties from their observations with, and instead go the other direction. We want to generate mock images based off of our simulation data. This has been work that's been done with, again, collaborators here at the CFA, and in particular I want to point out contributions from Greg Snyder, who I've worked very closely with throughout this project. So I think this is generally what sums up this next section. We have observers who know what they're doing. They've got these large telescopes. They're actually very carefully analyzing their data. And then here I come along just checking. I just want to make sure that this is sort of being interpreted in the most meaningful way possible. What we're trying to do is not redefine the way that observations are interpreted, but to rather see if we can bridge the gap in terms of how we can talk to one another. So when you try to perform these sorts of comparisons, if you take the simulations at face value, we're actually speaking somewhat different languages when we talk to observers. In the simulations, what we have is physical quantities, things like, for example, particle masses. We can get a galaxy mass by adding up the stellar mass in all of the particles in our simulation. That is not what an observer actually does. An observer has information about the light that travels to us, and then applies a model to derive the stellar mass. So there's some ambiguity about how we should actually bridge this divide, all right? In most of the simulations most of the comparisons I have talked about so far, I've implicitly assumed that all of the quantities derived from observations don't have associated errors. In some cases, they have error bars associated with them, but they can have intrinsic errors. Just to give an example, if we look at the galaxy masses that are derived from from observations, a change in the IMF alone can be a factor of 2 in the stellar masses that are derived. And that's not really something that we take into account. In the simulations, we do not have that equivalent uncertainty. So what we want to try to do is talk about how we can convert into a language which is more comparable between these two ways of doing science. So specifically, we're talking about bridging this gap by applying stellar population synthesis models, applying star formation rate indicators and morphological proxies directly into the simulation so that we can apply the same analysis tools that observers would use on real data. Now, we're not the first ones to actually do this. In fact, there's been a fairly large body of literature that has used mock observations of galaxies to publish results. This is just one relatively recent paper by Javier Arguedes looking at the Ares simulation, and on the left you're looking at a mock optical image of this galaxy where you see star-forming regions and an older, redder stellar population. This is another paper by Greg Stinson where they looked at these magic galaxies, and again you see the different colors for where you have ongoing star formation, and the redder population corresponding to an older population of stars. And this is work by Federico Marinacci looking at the Aquila simulations using Arepo with a fairly similar feedback model to what we've applied, where again you see bluer star-forming regions with redder, older stellar populations. In general, when people publish these sorts of models, they do so for a dozen, or at best 2 dozen galaxies. They're not doing these for entire populations. And so what I'd like to show you is that not only are we now actually able to obtain relatively realistic galaxy morphologies in our simulations, we're able to do this for very large ensembles of systems. So this shows a sample of morphology taken directly out of one of our full feedback simulations. This is showing one galaxy viewed from 5 different viewing angles. This is showing another galaxy here with a bar, again from 5 different viewing angles, and then 2 different ones down here which have more elliptical morphology. Right off the bat, it's important to note that we're finding both disk-like systems and elliptical systems directly in our simulations. In fact, this has been very hard to achieve in the past. These are forming in the same simulations we've applied the same physics, and so we can ask questions about how these have actually built up their morphological diversity. All right, that's what's shown here. So here, if I take a population of 5 elliptical galaxies at redshift 0, I can directly now trace back their evolution to redshift 2. One thing to note, this is showing rest frame GRI bands, Sloan images. So at high redshift, these galaxies appear bluer, and that's because they have higher star formation rates. Another interesting point is that if you look at these systems, 4 out of 5 go through what appear to be relatively major mergers before they reach redshift 0. And frequently, you actually see that that merger event is associated with converting what would be otherwise disk-like morphology into a spheroid. So we're now actually able to directly probe the transition of disk-like morphology into elliptical morphology directly in these simulations. You can also look at the assembly of disk galaxies. Here is looking at 5 different disk-like systems traced back to redshift 2. Now these are less massive systems, and so their merging history is somewhat quieter. But you do still see there are some mergers, and that's interesting that these galaxies are able to maintain their disk appearance even after going through a relatively major merger. But in general, the formation histories of these disks tend to be a bit quieter. So there's a lot of really interesting information about how, for example, mergers or in situ star formation is impacting morphological diversity. But really, the power of these recent simulations is not in doing this for 5 or 10 systems, but doing it for large ensembles of systems. So this is now showing about 25 galaxies from one of our recent simulations, traced out to redshift 2 with relatively fine time stepping. And we can just pan out to look at the galaxy populations that we actually have here. This is looking at a 25 megaparsec cubed volume, showing the 100 most massive systems. They're all fairly well resolved, and we have interesting mergers, interesting morphologies building up in all of these systems. For our most recent simulations, we did 75 megaparsec cubed volumes. In that, what we have is 7,000 galaxies, which are fairly well resolved. 7,000 galaxies with stellar masses above 10 to the 10 solar masses. We have more than 10 to the 4 star particles. That means we have fairly well resolved morphology. We also have some groups and clusters available in these volumes, which means that we can study things like what the environmental impact on galaxy colors or galaxy morphology is. Now, to show one application, one way we can actually use observational tools to reanalyze our image pipeline data. One game we can play is to rederive stellar masses for our mock image catalog. We already know the intrinsic masses based off of the simulation, but now we've created mock images so I can rederive the stellar mass I would assign to this galaxy as if I didn't know it in the first place. So we use the SED fitting code FAST to do this. What we're doing is effectively assuming a star formation history, in this case an exponentially declining star formation history, and then from that finding the best fit metallicity and star formation timescale to figure out what this galaxy's mass is. So this shows the fast mass against the subfine mass. This is basically the intrinsic mass from the simulation. And what you find is that we get a fairly good one-to-one correlation. However, this is actually shown over 3.5 orders of magnitude. If we instead look at the ratio of the fast mass to the intrinsic mass as a function of intrinsic mass, you do see there are some residual trends. And this, I think, is actually really interesting to note. You wouldn't have been able to do this if you didn't know the galaxy's intrinsic mass. Turns out the origin of this difference is actually fairly easy to tease out. We can look at the metallicity that FAST is assigning to these galaxies, the metallicity that the SED fitting codes thinks these galaxies have. In fact, there's a fairly clear difference between the metallicities that are found in this cloud versus what's found here. So if I pop back, you'll see there's kind of a relation of galaxies here, and there's another cloud of galaxies here. That's caused by different assumptions about the metallicity in the SED fitting models. If I look at the intrinsic metallicity, the metallicity from the simulation as a function of intrinsic mass, I find a relatively constant distribution. And so what's happening here is that FAST draws upon a set of stellar population synthesis models that have discrete metallicities, and they jump in fairly large intervals. And so what happens is that when I jump from one template to the next, I am moving in the right direction. These galaxies do have higher metallicities, but that discrete jump actually causes a kink in the masses that I'm deriving for these systems. If I come back here and rederive masses under the assumption of one fixed metallicity, this becomes a single relation. So I think that using this image pipeline data, there's actually quite a lot of science that we can do, and we've really only begun to scratch the surface. One thing that we can do is the SED stellar mass fitting. We find that factors of 2 errors are common. Overall, it does fairly well. Factors of 2 errors are common, and there are residual trends largely from the discrete metallicities in the stellar population synthesis models. You can ask questions about whether we get the disk elliptical fraction right, and Greg Snyder's working on this by using non-parametric fits for the galaxy images. We're also doing visual classification with Galaxy Zoo. We're going to upload a large fraction of our galaxies to the Galaxy Zoo project and have citizen scientists classify their morphology so that we can compare directly against visually classified survey data. And then we have other things that we can test, like, for example, how the high redshift merger rate is impacted by blurring of the images through low signal to noise or PSF blurring. So we can actually take our redshift 2 data and degrade its quality till it gets to observationally realistic level, and then see what fraction of mergers we're actually picking out. So these image catalogs are going to be made publicly available, and that's the way we hope to do science here. We're hoping that we can do some set of these projects ourselves but that observers who have tools in place to already quickly analyze survey data can easily adapt to also using these FITS files that we're providing through our image pipeline to rederive some of the observational quantities directly from the simulation. This has been set up with an SQL database that's hosted on an external server. We're now able to serve up the data directly from Odyssey, though. And so we can basically use our supercomputer here at Harvard to serve up data to people throughout the world. We've got pre-made PNGs, which can be used for visual classification, and we've got the raw FITS data, which allows people to look at these galaxy images in 36 different bands. So we're quite excited about the science that can be done there. I think that over the coming years, as simulations get larger and larger, and as survey data gets larger and larger, this might be the most powerful way that we can draw even-handed comparisons between these two types of science. So with that, I'll bring up the conclusions. There's a couple of points that I hope I've convinced you of today. The first is a demonstration of the importance of using an accurate hydrosolver in galaxy formation simulations. This really isn't an option. It can't be fixed by including stronger feedback or somehow circumventing this problem. Accurate hydrosolvers really impact the distribution of gas in and around galaxies. And without that as a basis of your simulation, you're going to have a hard time getting higher order effects right. I've showed that feedback is definitely necessary on top of an accurate hydrosolver to regulate the growth of these galaxies. And we've now implemented that into Arepo using a star formation-driven wind prescription and an AGN feedback prescription. With these feedback prescriptions, we're now able to get galaxy evolutionary functions that agree fairly well with observations in a lot of respects. And so we're now able to have populations of galaxies that we can very directly compare against observations. And in this last part, I've tried to demonstrate the potential of using observationally motivated comparisons to try to bring simulations and observations onto a more even-handed playing field. Thank you.
Thanks a lot, Paul. So any questions for Paul? Yeah.
How do you know that when you're comparing the mass you get from the SED and the plot you just showed a slides ago, that the disparity comes from the way you fit the SSD instead of the way you generate the SSD?
The reason for that is that we use this is somewhat of a circular argument, what we're actually applying here. We're using the same stellar population synthesis model to assign light to the star particles in our simulations that we're then using to derive the mass from the cumulative SED. The trick here, though, is that we assign light to each star particle individually. So we can assign light to each star particle unambiguously, given its age and its metallicity. We then add up the light contributions from all of the star particles and then rederive mass from the cumulative SED. And so we're applying the same stellar population synthesis model, we're just going in opposite directions. And so because we use the same model, we can say pretty confidently that we've assigned the light correctly. It's just a matter of the assumptions that are then made by the fitting code when it rederives the total stellar mass.
Going back to the very beginning where you showed the pyramid, you had gravity at the bottom and so forth. At the top, what sort of next steps do you envision with extra physics like magnetic field?
Yeah, magnetic fields will be tricky. There are. We talk about this quite a bit. I think that the next steps forward are refining our understanding of the feedback physics and how they're really interacting with the gas in and around galaxies. So right now, we have implemented a model which allows us to regulate the growth of these galaxies by kicking out wind particles. But the way in which these wind particles recouple to the circumgalactic medium, the speeds with which they exit these galaxies, this is not actually very well known. And so our model works in terms of regulating the growth of these galaxies, but we can do a lot of work to build a more fundamental understanding of how we think these winds are being launched and how we can then best realize them in these simulations. So I think that over the next couple of years, what we'll do is try to have more detailed studies of the feedback processes that launch winds on small scales and derive from that concrete prescriptions that we can apply back into large volume simulations to see how that impacts the galaxy populations.
How did you deal with AGN formation at hard registers? How far back did you go? Your clock stopped at about Z4 or 5.
So the way this works is to seed black holes instantly once a collection of dark matter particles, the Foff mass of the halo, grows above a certain threshold. So what you can basically show, though, is that given our black hole growth model, it's relatively insensitive to how we do that initial seeding, because black holes need to grow for some period of time before they actually become efficient at disrupting their host halos. So we've seeded them not at a fixed redshift, but at a fixed halo mass. And it turns out the way we're doing that is numerically stable, but it may not actually realize what's going on in the real universe entirely accurately.
Do you think that the discrepancy at redshift 1 is going to be resolved by a way that you can physics with the feedback you're already including, correct? Or do you think that it's actually a different, relatively different process at redshift 1 where the discrepancy are high?
Yeah, it's an interesting point to speculate on. I don't know exactly, but I suspect that a refined vision of galactic winds can do it. I think that the main component which we don't yet have a strong understanding of is when winds recouple, or when winds interact with the CGM or IGM just around galaxies, how that then impacts the subsequent accretion of those galaxies. That's where I think we have a lot of understanding to build up. And I think that if you're able to, for example, shock heat gas at the outskirts of a galaxy's virial radius, or shock heat the gas in the IGM just around a galaxy, you can slow the subsequent accretion rate, and that can be a very impactful way to slow a galaxy's growth that wouldn't necessarily be captured in our current scheme.
Or there could be a problem with the observations themselves.
Or there may be, yeah. 2 observers on the committee, I wasn't going to go there.
So a quick question, if you were to design the next simulation, or the very next one past the lustrous whatever, what would be the target that you think would be most beneficial to help address some of these questions?
So I think that Illustrious, if you talk about next generation simulations, to some extent Illustrious could just be rerun, but of course not with the same physics. I think the most interesting thing we can do moving forward is focus on how we actually improve the physics that we include in these simulations. If you want to talk about ways we can modify the actual simulation itself, there's 2 natural ways that you can go. One is to a larger volume. That way we sample a larger range of environments, and that could be interesting, especially if we want to talk about AGN feedback physics and how supermassive black holes are regulating the growth of the largest groups and clusters. The other way to go, of course, is to a smaller simulation volume, naturally, where you have higher resolution, and so we can do a better job modeling the ISM physics. Both of those could be interesting, but the real point that we need to focus on in the near-term future is getting the feedback physics right. And I think we're going to be best served doing that by doing really idealized tests of individual galaxies for a while and get a better physical picture about how winds are actually escaping these galaxies and how feedback from black holes is actually impacting the host galaxies themselves.
Any more questions for Paul? Yeah.
In your opinion, what are potentially some of the more interesting applications of this model outside of physics?
I have to. Thank you, Jared. So it's really difficult to say. I talked about the novel aspect of Arepo. The fact of the matter is that, if you talk about aircraft design, companies don't use SPH codes anymore. They actually use moving mesh type codes, right? So they're actually already using this in other industries. The fact of the matter is that this was the first time that a method like this was applied when coupled to an accurate gravity solver. And so the true novelty of this code actually is almost entirely constrained to situations where gravity is important. So maybe we could predict weather.